inviting us. My name's Jessica Robinson, and you're going to meet my husband Obin a little later in the presentation. We're so happy and excited that you invited us tonight. We've never done this format before. It's usually an in-person 45-minute to 2-hour presentation. I have a table full of my glass examples, and it's more of a conversation with people. Regardless, this is a great opportunity to learn about setting up photo equipment and how well glass glows on camera. So if we're all good, we're just going to get started. Tonight we're going to review 2,000 years of art, chemistry, and physics through uranium glass. I'm going to list everything by date to show how uranium and glass production has evolved. It's going to feel like a lot of information, but believe it or not, it's just the basics. All the dates and information we have for you came from researched documents. This presentation started out over an hour, but we did get it down quite a bit just to make it a little bit easier for everyone. So about me, I've been an avid collector of vintage items throughout my life and have spent the past 10 years actively reselling vintage and antique pieces. My passion for studying history led me to develop an interest in uranium glass and inspired me to share my knowledge with others. I love presenting information about uranium glass and hope everyone walks away with something new. Let me reassure you that we would never keep these items in our home if they posed any real risk or harm through normal handling. I'm super nervous about this stuff, but I'm comfortable with these items in my home. Everyone always asks, so I just kind of put it in the beginning that I am comfortable with it. And trust me, if I'm comfortable, everybody should be comfortable. So let's dive in. Uranium is often assumed to be rare, but it's more common than people realize. Imagine the whole Earth being made of tiny, mixed-up handfuls of dirt and rock. If you could scoop up 300,000 handfuls of dirt and rock, the tiny bits of uranium spread through all of them would add up to 1 handful of uranium. To get that same amount of silver, you would need about 13 million handfuls. Gold, 250 million handfuls. Uranium is more common in ordinary rocks and soil than many precious metals. So obviously it depends on where you're scooping, but it gives you an idea of how much uranium is really out there. Glass is a great way to track the use of uranium, as it's been made for thousands of years and it can be easily dated and tested. Analysis of glass from the 1st century Roman mosaics near Naples shows yellow-green glass containing over 1% uranium oxide. This shows that a few Roman glassmakers were using uranium nearly 2,000 years ago. But there's a debate if the Romans did it on purpose or if uranium was just kind of mixed in with everything in the environment. We're going to jump forward 1,000 years to the Navajo Nation in the southwestern United States. The Navajo people used yellow mineral pigments in their sand paintings, which contained uranium. And that makes sense, as they were using it for color, and it's so common there. We're going to head across the world, and 500 years later, silver mining began in the Yakimov region of what we now call the Czech Republic. Interestingly, miners suffered for centuries from mountain sickness, which was later discovered to be radon poisoning. Radon is a dangerous gas that is a product of uranium decay, which makes sense as uranium is often found near silver veins in the earth. In the 1600s, scientists such as Isaac Newton laid the foundation for our modern understanding of color and the light spectrum. These early investigations laid the groundwork for what we now recognize as fluorescence. From 1789 to the mid-19th century, 2 scientific paths converge: the discovery of uranium and the formal study of fluorescence. In 1789, German chemist Martin Klaproth isolated and discovered uranium oxide while analyzing pitchblende from the Yakimov region. Miners believed pitchblende was worthless, so it was often discarded. Klaproth named the new element uranium after the recently discovered planet Uranus. The only use for uranium at that time was colorant for glass and ceramics. Instead of it accidentally ending up in products, or sometimes it was used for color, it was actually isolated and identified at this time. German technical literature recognizes uranium oxide as a glass colorant by at least 1820. Within decades of Klaproth's discovery, uranium oxide transitioned from a laboratory experiment to a common artist resource used in glass and ceramics. Bohemian glassmaker Joseph Riedel intentionally added uranium oxide to produce vivid yellow-green colors, known as Anna Gelb and Anna Grün, named after his wife. These were the names of the first modern uranium glasses, prized entirely for their vivid yellow-green color. The Anna Gelb formula was used by the Boston and Sandwich Glass Company and later became known as canary yellow. I think many people who collect uranium glass are familiar with canary glass from the 1800s. By the 1840s, uranium glass manufacturing had spread throughout Europe, Russia, and China. Uranium was cheap, plentiful, and now a popular color. Fluorescence was also defined during this period. John Herschel demonstrated it could be triggered by ultraviolet rays, and scientist David Brewster observed fluorescent light originating from yellow canary glass itself and wasn't just a reflection. In 1852, George Gabriel Stokes provided the first complete explanation describing the wavelength shift, now called the Stokes shift, and famously called fluorescence darkness made visible. By the mid-1800s, uranium glass was a common product available to consumers, and believe it or not, many people knew it glowed. The early experiments with fluorescence used sunlight or candlelight. From the 1860s on, advances in electric lighting turned the glow of uranium glass into a public spectacle. Carbon arc streetlights became common and emitted a strong ultraviolet spectrum with a full spectrum of visible light. This meant shoppers could clearly see a bright green glow from uranium glass as it sat in shop windows. They absolutely knew it glowed, they just didn't know why. In 1885, Frederick Shirley patented a new type of glass he called Burmese and started producing it through the Mount Washington Glass Company. This is a great example of how chemistry in glass making was complex and practiced. The chemistry between the uranium and gold while being fired at certain temperatures is amazing. By the late 1890s, understanding uranium glass shifted from chemistry and economics towards the emerging physics of radioactivity. Between 1895 and 1898, discoveries by Röntgen, Becquerel, and the Curies revealed radioactivity as a fundamental atomic process. The Curies had spent years extracting tiny amounts of radium from the discarded pitchblende that came from the Yakimov mines. From 1900 through the 1910s, radioactivity captured the public imagination, leading to what became known as the radium craze. Radium was marketed as a miracle substance and appeared in watch dials, health tonics, cosmetics, medical treatments. And fun fact, it takes 3 to 4 tons of uranium ore to make 1 gram of radium. Not a cheap practice, but it was very popular. In the early 1900s, the term Vaseline glass begins to catch on in reference to uranium glass. This name originated from the resemblance of the glass's yellowish hue to that of Vaseline ointment. By the early 1920s, fluorescence research gave glassmakers new control over color chemistry, and uranium was no longer viewed as just a colorant. In 1921, an article in Glass Industry magazine reported a surprising industrial practice. Tiny amounts of uranium oxide were used as a decolorizer. This means the yellow-green color of uranium was added to some recipes to cancel out the unwanted red tones, resulting in a clear, almost completely colorless glass. Kind of the same as adding green makeup on red skin to make your skin complexion look normal. That's one of my favorite research discoveries, is reading how uranium was used to make clear glass, and I actually have examples of it. By the early 1920s, routine fluorescence testing showed that common glass colorants such as manganese, cerium, cadmium, copper, uranium, and sulfur all responded very differently under ultraviolet light. Manganese produced a greenish glow, cerium a violet, cadmium bright yellow to orange, copper red or orange, and sulfur a brownish orange. These studies showed that uranium glass was highly variable in fluorescence. The uranium glow was impacted by other elements in the glass such as iron or manganese. Between 1925 and 1929, glass makers pushed color chemistry far beyond uranium. They developed brilliant new reds and oranges using cadmium and selenium. Under ultraviolet light, many of these cadmium glasses fluoresced brighter than uranium glass. So yes, they knew it glowed. By the late 1920s, uranium oxide was sometimes added not for decoration, but to absorb and block ultraviolet light, as documented in a 1929 glass industry article. The 1930s are the most scientifically mature period in the history of uranium glass. By this time, glass chemists were systematically measuring fluorescence behavior under controlled conditions. By 1936, factory glass batch recipes, which are kind of the coolest recipes to read, show uranium combined with additives such as potassium dichromate to produce all shades of green glasses. These recipes show that uranium glass could come in a ton of colors: oriental green, pomona, Victoria yellow, and topaz are actual names of uranium glass recipes. The best part of reading these recipes is you realize the glow doesn't depend on how much uranium is in the glass. And not all green glows are from uranium. That's right, a brighter glow does not mean they dumped more uranium oxide into the recipe, but rather what's mixed in. And non-uranium green glow brings us to manganese. By 1939, glass makers clearly understood manganese's role, which was to control color in glass. Manganese was used to remove the green tint caused by iron, which was contaminating the glass-making sands. It is also used to create amethyst coloration, which became popular in the 70s. Did you know that manganese clear glass will turn purple when left in the sun for a long time? It was an actual fad in the 70s, which I think is pretty interesting. Manganese itself can glow green under ultraviolet light. And yes, it can be just as bright as uranium. Sometimes. In the 30s, green depression glass was popular because it was inexpensive and common. It was mass-produced and often given away rather than sold. Pieces appeared in 5 and dime stores, promotions in boxes of food. While pink depression glass was the most fashionable, green glass was the cheapest and most common. Can anyone probably guess why World War II would suddenly bring uranium glass and ceramic production to an end in the United States? The atomic bomb. In January of 1943, the U.S. government issued Uranium Conservation Order M285. This order immediately halted all uranium use in glass, ceramics, enamels, and glazes. This marks the clearest dividing line in uranium glass history. For the first time, uranium was valuable and was needed for something other than just making color. This did not affect the production of uranium glass in other countries. We have an example of a German clock made in 1949, which used natural uranium mixed in with the porcelain. Note I said natural uranium. The reason for that distinction is because starting in the late 1950s, uranium quietly returned to glass and ceramics in the United States. The return was in the form of depleted uranium. Turns out the waste product of uranium doesn't really have much value except to glass and ceramic makers. We see uranium quietly come back into commercial production as a cheap colorant, and we do have examples of 70s green glass that uses it. The public was not as accepting of uranium and radioactivity as it once was. The atomic age scared people, and popular culture made radioactivity scary, which is not how someone wants to sell glass. Since items were rarely marketed as uranium glass, many pieces from this era are unrecognized or actually misdated. The next element to mention is thorium. thorium entered glass much later than uranium, initially appearing accidentally around 1919. Thorium, a lightly radioactive metal, later became important in optical glass because it allowed lenses to be thinner, lighter, and clearer. At the time, glass makers were adding other ingredients to create special glass. Cerium and titanium-rich sands often contained small amounts of thorium, which entered glass unintentionally. By the mid-20th century, thorium was intentionally added to high-quality lenses, producing glass that is measurably radioactive and slowly yellows over time. If a thorium lens ever appears to glow, that glow comes from other materials and not from the thorium. By the 1960s and 70s, nuclear weapons testing, media portrayals, and radon awareness caused radioactive to become synonymous with danger. Consumers avoided uranium-colored wares, and manufacturers quietly removed uranium from product catalogs. And glass makers transitioned to substitutes that were safer to market or less controversial. Modern research has examined the safety of uranium glass carefully, and the results have been consistent for decades. Studies from the 80s and 90s show that uranium is locked into the glass and doesn't leach under normal conditions. It releases only trace amounts in harsh laboratory tests after the glass is largely dissolved. And I thought that was interesting because many people fail to realize this stuff has been studied. Laboratories have actually studied uranium glass and uranium ceramics. It concerned some people, so scientists definitely wanted to find out. Now, it's important to distinguish uranium glass from uranium glazed ceramics. In glass, uranium is mixed throughout the material. In glazes, it remains on the surface and may leach out if cracked or comes in contact with acidic foods. This is why uranium glass can be safely handled and displayed, but it's not advisable to use uranium glazed dishes for eating or drinking. The chemistry of many uranium glazes prevents them from fluorescing, either because the uranium is in a fluorescent state or because glazes rich in lead suppress the glow. We own several pieces with uranium glaze that are radioactive, but they don't glow under any type of light. In many antique household items, the most significant concern is chemical rather than radiological. Certain antiques may contain lead, cadmium, arsenic, or chromium used for coloring and glazing. I'm way more concerned about chemicals than the small amounts of uranium found in glass. The bottom line is, if uranium glass is stable and mildly radioactive, it's safe to hold and display with common sense care. In most antique collections, we should be cautious about chemicals and radioactivity, but they're harmless when you follow basic handling and storage safety. Whew. Okay, I told you it was a lot. We hit a lot of dates, and we actually barely scratched the surface. Now, I do want to show you a couple examples since we did talk about some things. So we're going to switch the camera over, and you can see my little special lot of display here.
Do you want me to turn the lights down?
Yeah, let's turn the lights down so people can get a better view of this glowing glass.
Oh, okay. Let me cut this down.
So as you can see, the glass glows as we turn the lights down and keep the ultraviolet light on. You get a better glow. So we're going to start out here. This is manganese. So this is an old medicine bottle, probably from the early 1900s. This bottle appears clear, but you can see it does glow green. No radioactivity. The next one we have here is selenium. Here's another example of an old medicine bottle that actually glows in a pinkish hue. I'm not sure how clear that is, but it is pink. And same thing, it just contaminated the glass process. Now this guy is cadmium. You can see the bright glow of this. And this piece is actually from the 70s. We jump down here to uranium. We get that typical bright green glow of the glass. And this is where the fun part is. This is the clear uranium glass. And you can see that glow is there. A lot of people would never even think to check this piece. Next we have radium. You can see the dial light right up. Now it's important to know radium wasn't just made into a gram and applied as paint. The radium was mixed in with paint, so it would go further, last longer, and they could cheapen it because it was expensive. And the last one is lead. Lead doesn't glow super great. It does glow blue, so we do have our little blue sign here to see this. So this is a great example of how many colors can work their way into your glass collection. All right, so we're going to turn the lights back on.
Okay, bring this back up.
The rest of the presentation will not be too exciting if it's in the dark.
Okay.
And if you want to give us a second, we're actually going to switch the camera back to the glass, and then I'm going to switch it over to Obin so he can give his part of the presentation.
Okay.
Okay, good evening, everyone. My name is Obin Robinson. I'm a United States Navy combat veteran with 20 years of service. More than half of that time, I managed hazardous materials and ran safety programs in dangerous environments. Between work and my hobbies, I have spent quite a bit of time working around radioactive materials. So today, I want to walk you through what radioactivity is in a way that's clear, calm, and a little enjoyable. Now, mind you, if you want a thorough education on radioactivity, there's a couple good 1,000+ page books you could read, but I'm going to summarize all that stuff into a really, really easy to digest manner. And let's start with the term radioactive. It simply means that atoms are unstable. They have too much energy or the wrong mix of particles, so they slowly fall apart. As they do, they release particles or energy that we call ionizing radiation. Ionizing radiation has enough energy to knock electrons off of other atoms. To detect ionizing radiation, we often use a Geiger counter, named after Hans Geiger. And let me grab my Geiger counter right here. So, this is a Geiger counter. This is one of the many we have, and I really like using this one because it's really easy to show people how this works. So, when radiation enters this tube right here, it triggers a tiny little electrical pulse, let's call it a little spark, a pulse. And that becomes the familiar click. So let me turn the sound on so you can hear the click in the Geiger counter. And what you're hearing right now is just the background radiation in this room. So what we'll do is just switch it over to the other camera, and you'll see that when I put the Geiger counter near something radioactive, it simply means more clicks are, there's more radiation over here. Here's that clear glass we're talking about. Here's the other uranium glass. You can hear it clicking more, and then we'll put it next to the radium clock. So all the Geiger counter is telling us is there's more radiation here or more radiation now than there was a moment ago when it starts clicking more. Now, Geiger counters have their limits. They cannot identify which radioactive element is present. They cannot measure uranium content. They cannot tell depleted uranium from natural uranium. And they cannot analyze the chemistry of glass or ceramics. So let's move for a second into the 4 common types of ionizing radiation: alpha, beta, gamma, and neutron. Alpha particles are simply 2 protons and 2 neutrons, and on an atomic level, they're heavy and slow particles. They're like the bowling balls of the radiation world. Alpha particles can only travel a few inches in air, and a sheet of paper or the outer layer of your skin can stop them completely. Outside the body, alpha radiation is harmless. Inside the body, it's a different story. Radium, for example, is a strong alpha emitter. The body mistakes radium for calcium and stores it in the bones where it causes internal damage. Radium-based luminous paints, like what you saw on the clock, they glow because alpha particles excite zinc sulfide crystals in a process called radioluminescence. That's not fluorescence. Radioluminescence is being caused by the radiation. The fluorescence you may see was caused by the ultraviolet light. There's a difference there. Now, most Geiger counters cannot detect alpha particles unless the source is extremely close and the detector has a thin mica window like the one that I showed you. Now, beta radiation behaves differently. Beta particles are high energy electrons or positrons. Beta radiation is like throwing handfuls of tiny pebbles against a large sheet of metal. Each pebble is small, but they're easy to detect when hundreds of them strike the sheet metal. Uranium glass and ceramics emit lots of beta radiation that can be picked up by most Geiger counters, even inexpensive ones. Beta particles can travel a few feet through the air. They can also penetrate the outermost layer of your skin, but they're easily stopped by thick glass, plastic, or metal. Now, gamma radiation, that's a bit more powerful. Gamma rays are pure energy. They have no mass and no charge, and they travel at the speed of light. They actually are a form of light, but it's not a type of light you can see. Gamma rays go through most materials like car headlights cutting through fog. The fog may dim the light a little, but it does not stop it. Gamma rays are the overachievers of the radiation world. They go wherever they want, unless you bring serious shielding to stop them. To reduce gamma radiation, you need dense materials like lead, concrete, or several feet of packed earth. Geiger counters can detect gamma rays at distances much further than alpha or beta particles can travel. Now, neutron radiation is different from alpha, beta, or gamma radiation. Imagine dozens of ice cubes sitting on a smooth glass table. If you slide one ice cube into the others, they'll bounce and ricochet. Some will stop and some will change direction and knock into the additional cubes in a big chain reaction. That's the neutrons bouncing into each other. Neutron radiation is a tiny part of the background radiation, and it's in the atmosphere. It's rare outside of nuclear reactors or specialized sources. So if we had a neutron detector, it might go off 4 times an hour or so. But if you had a neutron detector near a nuclear reactor, it'll be going off millions of times per second. So to slow down or stop neutron radiation, you need a lot of shielding. You can use thick steel. Hydrogen actually works great. What has hydrogen in it? Water. Water is a great way to slow or stop neutron radiation. Now, to identify radioactive materials more precisely, we use scintillation detectors. And let me grab the scintillation detector right here. So this is a scintillation detector, and inside the aluminum here is a crystal. And that crystal, when gamma ray hits it, there's a tiny little flash. And that flash is basically a burst of light when the gamma ray strikes it, and it can be detected, and we can also measure and plot the energy on a graph. So remember how when I had the Geiger counter on, there was only a couple clicks here or there? If I turn the sound on this rate meter here, you will hear every single one of those clicks is a gamma ray particle that's hitting the detector. So as you see, the scintillators are fairly sensitive. Now, to identify specific isotopes, we use a device called a gamma ray spectrometer. And let me show you the gamma ray spectrometer we have. This is a common gamma ray spectrometer called a radiocode. There's many different types you can get. We have other types, but this one's nice and portable. So a gamma ray spectrometer is going to take those energies and it's going to put them on a nice little chart. And it'll allow us to detect what type of radioactivity is coming in. So let me give you an example of that. So uranium glass and thorium glass both emit radiation, but only a gamma ray spectrometer can positively identify what's causing the radiation. So this chart right here is what you would see if we had thorium-232. Now take a look at that graph. This graph is what you would see from depleted uranium. This is just an example. We have many, many graphs of different ones, but you get the idea. If you see this on the spectrometer, thorium. If you see this, depleted uranium. So that can immediately tell the difference between what's in the glass just by looking at the graph. Now, radioactivity also appears in everyday materials. Natural background radiation, what you first heard when I just turn on the scintillator or turn on the Geiger counter, that varies all around the world. Ordinary glass and even your food can contain potassium-40, a naturally radioactive isotope. If this was of any concern, then every banana in America would come with a warning label, and they don't. Now, sensitive detectors can pick this low level of radiation up, but these levels are extremely low and they're not of any health concern. Now, let's talk about why glass containing uranium can glow. And not just the glass, but also minerals as well. When uranium is added to glass, it reacts with oxygen and becomes part of the glass itself. The uranium atoms in the glass absorb the energy from ultraviolet light, which briefly pushes its electrons into a higher energy state. So UV light basically gives the electrons in uranium glass a quick boost. Now they can't stay up there. When these electrons settle back down, they release that energy as visible light in a yellowish-green color. That is what we call fluorescence. So it's important to point out that this only happens when UV light is present. When the UV light is turned off, the glow stops immediately. The glow of uranium glass is not caused by radiation. That was radioluminescence, like what we would see in the radium paint. Now this brings us to some common myths that we're going to take care of right now. Myth number 1, uranium glass is dangerous to touch. That is absolutely false. The surface radiation levels are low and alpha particles stay trapped in the glass. Now myth number 2, it raises radon gas levels in your house. That is absolutely false. Any emission from uranium glass are far below any levels of concern. If you have radon in your house, it's from the natural environment, from the building materials. Uranium glass is not what is causing that. Myth number 3, uranium glass becomes less radioactive over your lifetime. That is false. Uranium-238 has a half-life of 4.5 billion years. That's much longer than you or I will be around. Myth number 4, if glass is radioactive, it must contain uranium. That is also incorrect. Glass can contain radium-226, thorium-232, lead-210, potassium-40, or rare earth elements that may be radioactive. Now, myth number 5. This is where it gets really tricky, so follow me here. 395 nanometer UV lights work best for detecting uranium glass. That is completely false. Remember, uranium glass and many uranium glazes glow when ultraviolet light excites the uranium compounds in the material. Tests show that this glow is strongest under shorter wavelength UV, around 330 nanometers. At that wavelength, the UV light has more energy and will make uranium glow much more clearly, including pieces that look weak or do not glow at all under 395 nanometer lights. So in quantum mechanics, light with a shorter wavelength has more energy per photon. That is a fundamental rule of physics. The common 395 nanometer UV lights are near the weaker end of the range that activates uranium glow. Because of that, they will miss some uranium glass or glazes, especially pieces with a lower uranium content or higher impurities. The 365 nanometer lights are what's widely used by collectors because they offer a good balance of performance, cost, and portability. 365 nanometer is also the wavelength that will excite fluorescence in other glass ingredients. So do not rely on fluorescence for positive identification. A 365 nanometer light paired with a sensitive Geiger counter will detect both fluorescence and radioactivity of uranium. Again, these are the laws of physics at play. It's not my opinion. Now, true 330 nanometer UV sources are usually specialized lab equipment. They're more expensive and not commonly available as handheld lights. But the science behind them is solid. Shorter wavelength UV reveals a wider range of uranium glass more reliably than 395 nanometer lights will ever show. If you want to do a quick experiment at home, take a 254 nanometer light, which would have made the lead glow. Try it on uranium glass, and you will see that uranium will glow even under much shorter wavelengths. Now let's move on to another myth. More uranium means a brighter glow. Completely false. The glow intensity depends on the chemistry of the glass, the oxidation state while it was being fired, impurities in the glass, and the glass composition, not uranium concentration. Iron, manganese, and chromium, for example, can all have the ability to reduce the glow of uranium present in the glass. What they'll do is they'll take some of that incoming UV light energy and convert it into heat rather than fluorescence. Now, what about the legality of all this? So across the United States and in Virginia where we are and in Arizona where most of our audience is, small amounts of naturally radioactive materials are legal to own without a license, as long as you don't change these isotopes or concentrate them. Shipping radioactive items is allowed with proper labeling. Flying on an airplane with radioactive items is tricky because radiation detectors at airports are extremely sensitive, so mailing the item home is usually safer. Driving with small sources is legal when they're sealed, labeled, and stored safely. Now, if you want to find natural uranium minerals, the U.S. Geological Survey provides excellent tools. Go to mrdata.usgs.gov and ngmdb.usgs.gov. When you go there, you'll see maps that show natural radiation from surface rocks. They'll point you in the right direction, but they won't guarantee valuable deposits. Make sure before you go to anywhere indicated on the maps, you check the land use rules. Only collect the minerals where you are allowed to. Only pick up rocks from the surface and never enter any old mines if it's unauthorized. This is dangerous and often illegal. I like to remind people that if a mine opening looks like the opening scene of a horror movie, that's because it is. Now, even though the uranium glass, ceramics, mineral specimens, and radioactive sources Jess and I own pose a minimal risk, we still follow ALARA. This stands for as low as reasonably achievable. We handle the items only as long as needed, we keep our distance from them, and we maximize the shielding when it's practical. We store dusty or crumbly minerals in closed containers, and this keeps the exposure level at a very, very low level, which we're comfortable with. Now, before we finish, we need to inform you about rare earth fluorescent glass. Many bright green glowing glass pieces, especially newer ones from China, contain rare earth elements like terbium, dysprosium, and erbium. These elements glow intensely under 365 to 395 nanometer UV light, and they're often mistaken for uranium glass. Separating rare earth elements from sand and ore is difficult. China invested heavily in rare earth mining decades ago. This gave Chinese glass makers easier access to the materials needed to make this glowing glass. Now, rare earth elements love to show off their UV fluorescence. They will glow at the slightest excuse, and we actually have an example of this glass. These new glowing glass items have been tested thoroughly. The results are consistent. The radioactivity comes from thorium and not from uranium. These new glass pieces that glow under 395 are not uranium glass, even though they may set off a Geiger counter. So Jess, if you want to switch it over to the camera, I'll show them. Inside here is one of these newer pieces of the glass that actually contains thorium. So it will glow brightly. And look at that. It'll glow just like uranium glass. Actually, it looks like it's even glowing brighter than uranium glass. But this is not uranium glass. This is why fluorescence and radioactivity must be treated as separate phenomena. Some glass glows, but it isn't radioactive. Some is radioactive, but it doesn't glow. Some glow and they're radioactive, but it doesn't mean they're uranium. The best and least expensive non-destructive way to know what you have beyond a doubt is through gamma ray spectroscopy. It will never fail you. So, Tonight, we trace a story that stretches from ancient Rome through scientific revolutions of the 1800s, through industrial color chemistry of the 20s and 30s, through wartime uranium controls, and into the modern era of radiation science. We've shown, both through historical and modern context, tools that uranium glass is safe to collect, and it's endlessly fascinating. We've also shown you that the glow does not identify uranium, radioactivity is natural, and the chemical composition is often more important than radiological effects. So, this is a hobby of learning, science, and historical appreciation. Thanks for joining us, and we'd love to hear some of the questions. So, right now, if you want to give us a call up, we can take some of the questions from the audience. For some reason, YouTube is not allowing brand new broadcasters to have a chat, so sorry, I don't control YouTube.
I'll switch the camera.
Yeah, switch the camera over, and actually, if Sean, if you want to call, we'll see if there's any questions from the audience. Let's see. So we do have many different radioactive sources and many different types of glass that we could show. Oh, here he is. There we go. Hey, how's it going? Can you guys hear everything? Okay. Jess is putting some of the other glass examples on the table. Did the audience have any questions? Is mostly history. Yeah, he's taking a couple of questions he's seen.
Obin, how did radioactive rocks containing uranium or thorium, how did they originally get so radioactive?
Oh, okay. Actually, that's a fantastic question. I love this. Okay, so how...
Obin, repeat the question.
Okay, so the question was to Jess, how did these rocks originally become radioactive? So the latest data on how they became radioactive is actually thorium and uranium was born in the collision of neutron stars. So deep in outer space, neutron stars were colliding, tearing themselves apart, and this dense material from the stars found its way through the universe as the world was being formed and cooled. So what you see of the uranium and thorium here on Earth actually has its origin in deep space. Basically, the glass that we have and uranium you see, that's bits of dead stars, so to speak. So hopefully that answers your questions. It's very fascinating. It's actually a fairly new scientific discovery in the past decade. Mm-hmm.
And in our solar system, the Earth is supposed to be outside of what they call the frost line.
Yes.
So all of water on Earth is supposed to be frozen. The reason it's not is because Earth is warm. And it's because Earth has enough uranium and thorium that it heats up. That's why the Earth is, magma in the center, molten. There's enough uranium and thorium to heat up the Earth enough. That's why we have to in the position of the solar system.
So what I'd like to point out right now is Jess is going through some of the different types of glass we have. One of the ones that she's showing right now is actually the depleted uranium glass. Yeah.
That's very rare.
And that is basically the waste byproduct of when you're trying to make nuclear fuel. That's what's left over. Chemically, it's identical to the mined uranium, so glass makers can still use it. And what she's going to show you next is actually slag glass. So this is a vase, which is slag glass, and this is uranium glass as well. Beans right behind you. And you may see a tail in the corner. That's one of our cats. It's very inquisitive. Sorry. Any other questions from the audience?
So I think here in this town we have big slag piles. Obin, we have big slag piles, but can you tell for everyone what exactly is slag glass?
Oh, okay. So, I guess the easiest way to explain a slag glass is it's a junk glass, so to speak. These are the pieces that are left over from other glass making activities. And these are the pieces which a glass maker can basically remelt and turn into a new piece of glass. And yes. And did you guys catch when we were talking about the clear uranium glass? Did you catch that? Yes. And this is something which was hotly debated, and we have some of the slag pieces we have are clear uranium glass. This is a plate which we believe the uranium also got in there because that same plate is available as a uranium glass plate, so some may have been left over in the mixture, but the uranium was used as a decolorizer for that glass. I'm not sure if you saw it, but also Jess showed some of the carnival glass. If you look on your camera, the piece that's all the way towards the 9 o'clock position, that is uranium glass, but due to the composition, the glaze is, the coating of the glass pretty much completely suppresses any fluorescence. This is uranium glass, but it doesn't really suppress. This is what we're talking about, where 330 nanometer would be better to light this up. 365 barely has enough energy. 395 will not show it. But if people are wondering, the way we know this is uranium glass, we use what's called a GS Max 8000 spectrometer, and it can count like 200,000 plus gamma rays per second. So we put these items in a lead castle where there's heavy shielding, and then we analyze them for 2 to 3 days at a time. And we get a background reading, we compare them, so that's how we know this is uranium glass. Did anybody have any other questions on the glass, or did you want to see some of the the element and mineral examples we have? Okay.
So he's a rock carver.
Okay.
He does rock carving.
Mm-hmm.
So he's grinding away and making dust on a pretty regular basis.
Mm-hmm.
Some, petrified wood. He wants to do some fluorescent stuff. How dangerous is that to him?
Oh.
And how would he know? And what can he do to mitigate the dangers?
Okay, so if you are grinding rocks, especially ones which may contain uranium, one of the places that you can actually look for some really good filters. Go to any place that works with woodworking. There's the Woodcraft store, for example. They have filters that you could put right in your work area that will suck up any of the particles that are generated, and they'll trap them in a filter, and they'll exhaust them from your work area. The other thing you can do is wear a simple N95 mask, like what a lot of people had to wear during COVID, or an N100 mask as well. You don't want to breathe any of those particles in, because they can cause to put me on the spot here, silicosis or something like that. It's basically a disease that miners would get from breathing in a lot of these particles, and also some of the people that work with granite countertops will also experience that too. So just to go back to what he's asking, I would look at some of the woodworking and woodcrafting places and look for the filters and workspace exhaust systems that they have, so that way he stays safe.
I'm going to expand on that a little bit.
Okay. Okay.
So, if you go and touch radioactive rocks, you're pretty darn okay. Like, it's not really going to get through your skin. It's not really going to hurt your body. You can sit and hold pretty much any of those perfectly fine for quite a while. Now, don't sleep on, on your
No.
pillow. You can hold them for hours and hours and hours, day in and day out. You're going to be pretty darn okay. The problem is when it gets inside your body. And the easiest way to get inside your body is dust. So anything you can do to mitigate that dust, including water. I don't know if different kind of burning you do, if you're able to dribble some water or even keep a mist over it. But it's probably a good idea.
Yeah, definitely.
It's radioactive. Most rocks actually can still be pretty bad or worse than radioactivity because of the heavy metal content.
Yes.
Uranium is actually more harmful to the body as a heavy metal poisoning than it is radioactive. If you want proof of that, there's a reservoir in northern Colorado that just opened up for drinking water, and they noticed it's too much uranium. It's not, and they're not putting it to human consumption right now because it's not safe. Radioactivity is not the issue. Heavy metal poisoning is the issue.
Yeah, actually, if I could add to that about the heavy metal poisoning, so you see Jess is illuminating the cadmium glass and the selenium and the lead. Those are very toxic. As a matter of fact, you can go to National Institute of Health, and they will show you all the different toxic effects from cadmium and from lithium and some of these other elements if you ingest too much. I agree. With uranium, it's not the radioactivity you need to worry about, it's the chemical hazard, but the chemical hazard of other elements are actually far, far worse. So we have a lot of uranium glazed ceramics. Do you see the little dog that's sitting on top of the uranium element symbol? That dog is actually uranium glazed ceramic. It does not glow at all. No UV light will excite the glow. We think it's because there's probably a heavy lead content when this was being made, but this does contain uranium. So that's why we warn people, uranium glazed ceramics have the ability for you to ingest uranium and other toxic elements. So like, for example, you may know the Fiesta Reds, those bright orange and reds, they actually contain a lot of cadmium and lead, and they can contain things like arsenic, which are actually much more toxic for you. And thanks for that question. That's actually a really good one.
Carnival
Oh, okay. The carnival. So the carnival glass, where you'll usually see, she's never seen any food in carnival glass.
Ah, so that's interesting. So carnival glass actually expands to a lot of different types. A lot of them were decorative. So this is a great example of a carnival glass bowl. What you most likely would see is this on display, and the most somebody might put into it is hard candies or nuts, but the inside design, no one would want to cover that up. Now that being said, there is very plain carnival glass, but it was more of a decorative thing. It was meant to show off and to kind of, see that you got fancier glass. I'm sure people have used it for food and water consumption. There's always that one person who drinks out of a gold cup.
Does all carnival glass contain uranium?
No, not all carnival glass contains uranium. We recently went to a auction that had one of the largest carnival glass collections the auctioneer had ever seen. And I would say out of 300 pieces of carnival glass, we were maybe able to find less than 20. The reality is uranium naturally makes its way into the glass making process in that period of time, and it was a colorant. So it makes sense it's going to be in there, but it just wasn't what they meant to do. So most carnival glass is not uranium. And sorry to yell, it's hard to tell
Yeah.
between the phone
Those
and
are the
everything.
phone. Did they want to see any of the sources before you guys logged off?
Do you want to see anything else in this collection, including sources which are basically cesium, which you can find in different rocks, purified into just a cesium mesh. You guys want to see that? Sure.
Okay. So Jess, what we'll do is we're gonna switch over here. Jess, start taking some of the glass off and just kind of hang out, and I will get my cesium and I'll get some of the other sources out so that way people can see the radioactivity level in them. And give you a second here. I'm putting on some gloves in the background because this is part of that ALARA principle. We want to stay safe when we're dealing with these radioactive elements. So actually, the first one I'm going to bring out is depleted uranium. And I'm talking about pure uranium metal. And this stuff is fairly radioactive. Actually, Jess, you want to give me a knife to open this? And
I'm going to switch it to the camera.
yeah, switch it to the camera. So this is uranium metal, and this is pure depleted uranium. Where this came from was actually, let me turn the phone down really here. And this came from East Mountain Scientific. It's 29 grams of depleted uranium. And what I'm going to do is I'll open up the container so you guys can see actually what it looks like. And this is where we bust a couple myths here. And also, let me get the Geiger counter too, so you can see. The Geiger counter, I'll turn the sound on, and can you hear the clicking? This is the outside of the container. So on the Geiger counter, I'm getting, let's see here, 106 counts per second. Let me open up the container. Carefully, very carefully. And I'll show you what the uranium metal actually looks like. So, this is pure uranium metal. And it's basically, it's pretty heavy. It feels heavy for its size. This is 29 grams of depleted uranium. So let me show you what happens. This is stopping the alpha particles, but check this out. We're now up to about 5,300 counts per second. And what I can do is if I get, let's see, actually no, yeah.
Ready?
Yeah. Well, actually this is, so we'll show you, the gamma rays are still getting through some of this. So put paper there. See, it's not going to slow down the gamma rays. But grab me some of the metal we have here, some of the shielding. Let's put lead in between. Jess, if you hold the lead. So, see that? Now move the lead away. Put it back. The lead pretty much stops the radioactivity from getting through. And this was a fun little acquisition because people are just like, oh, what's uranium look like? No, it's not green. It doesn't glow in the dark. It literally just looks like a slab of dark gray blackish metal. The reason why it's in the plastic bag is because uranium oxidizes very quick in open air. So this is actually sealed with an argon gas to prevent it from oxidizing. If I didn't do that, it would corrode and crumble very quickly. The next one I can show you is thorium. So this in here is a thorium source, and this is thorium-232. So again, a fairly unremarkable black metal. Now watch this. You can hear the Geiger counter, and you can hear it's pretty radioactive. Not nearly as bad as the uranium was. Will the sheet of paper stop it? Nope. The gamma rays go through the sheet of paper, but take the lead. There you go. You see it stops. That shows you lead is an excellent shielding against gamma radiation. Now, thorium, as we mentioned, was used in the glassware, and it makes lenses lighter and much sharper. And I guarantee you, you've seen many, many movies which were shot on thorium lenses. If anybody's a sci-fi fan, the movie Aliens was shot with thorium lenses. They're actually very common. And there's several YouTube presenters that shoot all of their stuff on thorium lenses. So they're pretty cool. Now, cesium-137. This is not a naturally occurring element. This was made in a nuclear reactor. So with the neutron bombardment, they take other elements and they bombard it with neutrons in a nuclear reactor or a high neutron source, and they make cesium-137. Now, this stuff, even though it's in the lead castle right here, let me show you what the Geiger counter does. Oh, don't want to drop there. This is what happens when you hear, when you can see how much radiation is coming out from the source. And the paper doesn't stop it, but grab the lead, and you can see right there. That's why we store the cesium in these little lead pigs, they call them. They call them lead pigs. I didn't name them, just call them pigs. Now, also here, I have europium-152. So you may wonder, how do I know my gamma ray spectrometer is accurate? This is a europium-152 that's in here. And when I look at the peaks, I basically look at the peaks from the energies, and I line them up to say, okay, well, this is supposed to be at this energy level, that's that energy level, and that's how I calibrate the spectrometers. And here, you see, it's not that radioactive, but again, if we put the lead in front of it, it would slow it down and stop it. So I actually have a pretty interesting source here, which not too many people have seen. This is pure radium. Yes, the radium that you saw on the radium clock, I have a radium source right here. Now, this stuff, there's a reason why I have gloves on. You don't want to touch it. Radium's not good for you. Even in this form, I don't even want to risk getting it on me. So, radium, it's fairly hot stuff. I'm going to take the top of the container off, and right here, you hear the Geiger counter is barely clicking. Now, when I expose it to the top, listen to this. My Geiger counter right now says over. In other words, it maxed the meter. the amount of alpha, beta, and gamma radiation coming off of this thing, the Geiger counter doesn't go that high. It will max it. And I have actually my other Geiger counters are going off near it saying, hey, you just exposed a very powerful source. Now, what does it look like? I want to see if I can tilt it towards the camera. Actually, Jess, bring it to the other camera. This is what radium looks like. You see that? Very exciting, isn't it? It looks like a tiny little watch battery. That's it. There is no glow from radium. If you put a light on it, you're not going to see the radium glowing. Nope. Anything you see in there is going to be just from the paper that's lining the inside. That's why you have to mix it with a paint in order to get radium to glow. So, one more one I want to actually show you is nickel 63. This is a beautiful way to explain alpha particles. Remember how we said that alpha particles will be stopped by a thin piece of paper? So here's where we have, I don't know if you can hear the Geiger counter going off right there. Now, piece of paper, barely any clicks. So what it is emitting is alpha particles that are only traveling a short distance and they're being stopped. If they're not being stopped by the air, they're basically barely getting to the mica. The other thing I wanted to show you here is if you go out near you, I can't guarantee this is what it's going to look like in your area, but this is actually uraninite. This is what uranium is going to look like in its natural state. Not really too exciting. It looks like a fairly boring little rock that you'll see somewhere, but then we put the Geiger counter up to it and that is uranium. And we can confirm that with a spectrometer. So again, I know I can keep everybody here. This is why Jess says in person, this presentation, we usually time it to be 40 minutes and we've had it go as long as 2.5 hours because people just kept on asking questions. I don't want to keep everybody all night, but are there any other final questions or anything else you'd like to hear? Does that switch it back?
Or anything else? Does that switch it back? No, I think that's it, Obin.
Excellent.
Might be time to wrap this up, and thank you so much for showing us all that very interesting stuff.
Okay. Well, thanks so much for inviting us, and we're glad that you guys could watch the presentation. I do want to say that don't cut your feet off just yet, because there are always those people that say, well, how do you know this stuff? How do they know this stuff? This is based upon a lot of research through cumulatively what is tens of thousands of pages of documents. And people always say, show your sources, show your proof. So in our little outro, we'll actually scroll through the sources that we use to create this presentation. So if there's no other questions, I'd say as soon as you see the credits finish rolling, then I guess you guys have a great night. Thanks so much for inviting us. And if anybody has any follow-up questions, if you can give them our contact information, we are more than happy to answer any follow-up questions, including any lingering ones they may not think of right now. Okay, so like I said, we're going to roll our credits here, and you guys have a good night, and I guess I will talk to you later, Sean, okay?
Thanks, everybody.